So last time we talked about functions, how to define functions, what is a current function, what is a partial function application, and how to use them in practice. This time we'll talk about types and higher order functions. So this whole thing has the goal to write robust code. We don't want to have null reference exceptions, we don't want to have unhandled exceptions, and we want to have the code to be as much as reusable as possible. So we want to have small, reusable, testable parts. And we don't want to repeat ourselves. To this end, in this lecture, we will use types to tackle the first goal. And we use functions to tackle the second goal. The goals of this lecture are based on two functional programming concepts, which is the first one is the algebraic type system, which most functional programming languages have, and higher order functions, a key component of functional programming, as we have already seen in C# and LINQ and other applications. So what we'll do next is we'll look at the algebraic type system, and at some points we'll also look at other languages and how those concepts can be used in other programming languages. So let's start off with algebraic type system, which actually in this case is used for us for removing nulls. So there's a popular talk by Tony Hoare. He's the one, he's famous because of many contributions to computer science, but one of the most popular, for example, is the Hoare calculus for program verification. And he's also, he might be not too proud of this, but he's very famous because his talk, the $1 million mistake, which is linked in the slides, where he is talking about null, why he introduced null in the first place in the what was the programming language? I'm not sure. In the first programming language he worked on, and yeah, you can look at this. So what are the sources of null? Basically, we have nulls because we have uninitialized values. For example, when we create an array of objects, all of those objects are null from the beginning. So sometimes it's easily preventable by, for example, using assignments when constructing the value. However, sometimes it's not that easy, for example, for arrays, especially when we don't want to pay extra for running over the array and initializing it. However, for example, in F# arrays should be initialized, for example, by array.create, which also takes a function how to initialize each element of the array. Sometimes we use a null on purpose, then we forget that we used it on purpose and we get a null reference exception. However, we would like to get rid of this. And there's also another case where we use null to encode failure. This is more like from the C world, where null is often used as encoding for something which has not worked. However, all of those use cases should actually be circumvented by taking a different approach. And in the next slides, we will present basically the basic approach to one basic approach based on the type system to get rid of nulls. So what happens when we don't have null? We need to model it explicitly. When we look at, for example, C++, there we have rather new construct, which is called optional of int, and we can create an optional by using the function make optional. Then we get out an optional. We can check if there is a value in the optional. If there is, we enter this path, and by using, for example, in this case, we use star b, and which dereferences b, and since we are here, we know that it has a value and it returns. When we create an optional without making it carrying a value, we end up with an optional with no value. We can still use here different dereferencing of this optional. We get crazy result in that case. So this is basically an unsafe way of accessing the underlying data. In functional programming languages, we often use discriminated union to model exactly this in order to make it impossible to dereference an optional without checking it before. When we look at Haskell, for example, we can read this in Haskell. The type is called maybe. It's instead of optional, it's called maybe, and it's basically a type which contains a value. So the type contains a value sometimes when it's just, or it's nothing, then it has no value. So this is basically the discriminated union definition of the option type or the maybe type in Haskell. Let's look at discriminated unions in more detail. We will switch now to the F# definition, which is pretty much the same. So what we can see here is that we have a so-called union type or discriminated union, which is basically just like a class definition. Here we have those tick A, which means this is a generic parameter to this type option. Without this tick, we would write like class option of A in this way in C# or in Java. So basically, this is the type name of the type we're just defining, and those are the two constructors for the value. So we can either use sum and give it a value, then we get out an option, or we can use none to create a valid instance of the option type, however it has no value. So when we look at it in the code, let's see. What we can do here is, let's define option A, it's generic. This is the type. We have two constructors. The first one is sum, which is the constructor when we have a value. So here the constructor now carries this data. And here we have none. So please be precise about the wording here. This is the type, and those are the constructors. So basically what we can do here now is we create an option. Let's say A is an option of int, for example, by just calling the constructor none. So here now we arrive with our value, which is a legal instance of option. However, what should be clear here is that this B has no value, so accessing it won't be possible. We can create another value. Let's say this is the other one, and here we use the sum constructor. So 1 gets this value A, so we get out an option of int, and this is the return type as well. Since we are using F# here, we have type inference, and we can just write sum1, and it will automatically infer that we have an option of int here. So great. What can we do with this option type? Basically, this thing here, like calling the constructors or using the constructor, is called construction. And there's the opposite thing, which is called destruction. So what we can basically do here is we can match by pattern matching. We can match on the cases, the constructors of the union type, by using the match construct. And when B is none, we say okay, no value. And there's a second destruction possibility, which is when we have a value, then we have here the value. And here, let's say, okay, we take the value and make it toString. So what we can see here now, let's execute this code. We have the definition of the option, we have the value B and C, and we get the result no value. We can also put this into a function. Let's say this is our function which takes an option of int and then performs the pattern matching. And here we again need to use the argument here. What we can do now is we can just define the function, and then we can call foo on, for example, none. We get no value. We can also call it on a value called like this, sum1. Then we get out 1. And when we do it like when we put in a string, this one fails. However, we could just redefine it like this. Now we have a variant of foo which works in strings. Or we can also define it generically by saying, okay, we have here the type A. Here we get out A, and each A in .NET is toStringable, so to speak. So we can have now a function from option of A to string, and each time there's something in the function, in the option, we get the result. So we get 1 here, or we get hello here. So great, let's look at the anatomy of this thing. So when we look back, we have construction, and construction is done by using one of the constructors. And each constructor is separated by the bar, which already indicates that it's something like or. So either we use this constructor or we use this one. And when we look further, the destruction is exactly the same. Here we have our string function, which takes the option, performs pattern matching. Since the construction is either this one or this one, we also need to take care of those different variants we have. So we have sum v, do it to string, and we have the none case. And what's important to note here is that we often talk about destruction, construction in functional languages. We really mean the semantics of construction and destruction, and not the underlying operational semantics as we have it in C++, where we talk about destruction when we talk about cleaning memory up or freeing some resources. Anyhow, pattern matching is the way to go. It's often the way to go, and pattern matching is much cooler than you might think of. Let's say we have a function prettyPrint. Move it down here. We get in an option of int, and now we perform pattern matching on O. What can it be? Well, it could be a sum. Here we can either put in a variable, or we can also put in a value, which means that this match case only reacts to this, or only responds to really this actual value. So here we can say this is 1. We can have another one. This is for 2, for example. Or we have, when we don't care about them anymore, we can use this generic variant here. Here now the value gets bound to the value C, to the variable C, sorry. So, and then what's cool here is that we get incomplete pattern matching warning here, which actually should say that a particular case was not handled. When we look at it here, for example, the value none may indicate cases not covered by the pattern, which means that here we get a kind of completeness check. So we need to add the missing case, and this works really deep. So here could be another structure and another structure, and we can really look into the structure and inspect the actual data of the structure in a very concise way. What we can also do here is we can, for example, define functions as such. We have A, this is a bool, and B, this is a bool. So here XOR is which returns a bool, and XOR is basically defined by doing a tabular lookup. Or we can define it as such, And what's cool here is that we can also pattern match on multiple things at the same time. So what we can do here now is when the first one is false, the second one is false, we also get false. When we have the first one is true and the second one is false, we arrive at this is true. And then we have, for example, when we have false and on this side true, it's also true. And when we run this function, we quickly find out that we are missing a case. Actually, it's indicated here. We are missing the case true. So when we call this function, let's define the function. Is it here? When you say okay, is true and false? Yeah, it's true. False and false is false. What's about true and true? And here we get an exception, but we were warned beforehand about this exception. So basically, those exceptions never occur because before running the program, we fix all warnings and say, okay, the true case also needs to be handled. And this is really an underestimated feature in programming languages, the pattern matching. It's really, really useful, and it's getting more and more into mainstream programming languages as C#, where we will see pattern matching, I think, in version 8 or 9. So typically we have a kind of a strange feeling about case distinctions, and we often think in software development, is every case distinction or every if leads to an error at some point because something gets wrong all the time. In fact, there are some cases where we need case distinctions, and this is also kind of dictated by math, where we already use case distinction. The thing here is that case distinctions should be really flexible and easy to use and without much boilerplate. This is exactly what functional programming languages bring us when talking about discriminated union, because they exactly built for doing case distinctions. What's the background of this? Those as we often call them union types, because they are a union of different cases, have a long history. They have appeared in Algol in 68, for example, as the term tagged unions. Then in Pascal or Ada, which has a strong type system, they had variant records. And it's also became popular again because Rust and Swift, for example, have support for tagged unions. And this is the tagged union used in Ada, where we can define a node which is a union of real integer, complex, or a string, and we can already do pattern matching on this one. So you might now think of, oh, this is not really new. C++ also has unions. It has it halfway, because when we look at C++, you can define a union which actually is either an integer, float, or a double in that case. However, you need to manually track what of those is actually within this value. Otherwise, you get crazy results. How does it look in other languages? For example, here in Swift, we have discriminated unions, whereby here we shall note that the first case here we have a barcode. The first case is QR code of string. So here this variant contains a string, as it's very, very similar to what we had in option, where we had a general A contained in the case. And here we have an additional case, UPC here, where we have 4 arguments. So typically union types can also, or discriminated union types can store multiple values per case, but we will see this in the near future, and what's the base behind of this. So what happens when we have a lot of options in our code, and we take it seriously, and we use options every time we might not have a value. We often need to take care of a lot of of options, and we need to pattern match a lot. So even though pattern matching is awesome and very powerful, it will get repetitive soon. So what one typically wants to do is to abstract over this pattern matching as such, since it's often reoccurring in our programming experience. And what's the main idea of or what's one of the approaches for functional programming languages when we see that there is duplicate code? Well, as we have seen in when programming with LINQ or with lists and streams, every time we have repeated code, we try to synthesize a higher order function out of this code in order to get rid of the repetitive pattern. For example, here we could define a function, let's call it map, which takes a function from A to B and an option which is an option of A. And what's the result I would like to have? I would like to get out an option of B. However, this now defines pattern matching once, and we can reuse it multiple times. So let's say, well, how could the definition of such a function look like? Well, we get in an option. What can we do with an option? We can do nothing else with a function. We can do nothing because we have no A. With the option, we can actually just pattern match. So what we basically do here is we just take, okay, let's say we do a pattern match here. We get the value here. In this case, this is the first one. This is if we have a value. If a value of type A, well, what can we do now? We have now an A, we can call the function. However, we would like to again return an option, since in that case of we have no value, we can do nothing except for producing nothing again. So when we have something in our option, we can call f on A, but again wrap it into an option to have it have the same return type for each case, which needs to be there. So what we can do now is, let's say, okay, I'll just quickly show you a quick hack function to show you the interoperability with .NET. Let's say we define a function, let's call it parse option. This one takes a string and returns optionally an integer, but only when this string is parsable. So here strings in .NET strings can be parsed by using try parse. To open system here, because try parse is defined in system. Oh no, it's called like this, int try parse or parse. As this might fail, and there's also exception handling in F#. I will just quickly use it as here, which is when there was a parse failure, we return none, and we have, if it works, we return some. So here we just made the transition from exceptions to option. So this function now is total. This was actually unnecessary. What we can do here now is, oh, it was not unnecessary. What we can do now here is we can define the function and say, okay, let's parse an option. Let's parse the value and return an option. Let's say this is 1. We get sum 1. Let's say we have a floating point inside. This doesn't work because it's not an integer or also a string. So here we have a save parse function which returns a value for every input, which means, as a side note, the function is total, which means that for every input it at least returns a value. As opposed to int32.parse, which might also fail in executing and just throw an exception, so it never comes to an end. So the function does not terminate. So now let's define a function we have we use is our map function. We map over the so what do we do? We parse our input s, and then we map over it. So instead of what we can do now is we can do, okay, let's parse our value. When it's none, we say it's none. When it's some, then we say we add 1 to it. So this is the boilerplate version where we have the pattern match, and when we have an additional operation which is chained after this one, we again need to do pattern matching, because every time oh, there was a mistake. Every time we execute a function, we get the option type, and we always need to pattern match. So when we now apply our map function, we can write it much denser, like say let's parse +2. We get in a string. What we basically do is we parse the option of the string, and then we use the map function, and we map over what is the first argument, a function, which in that case is the parsed value. We do v + 1, and then comes the option. Oh, we need to name it differently. So what we have here now is we have a we need to put in, what's here? Our map is not defined yet. Let's define map, and then let's define this function again. So parse +3 with the value 1 results in 2. And what how can we write this differently? Yes, we have seen in the last lecture that piping is a rather nice construct to refactor code. So let's say we write parse +4, which takes a string. We take s, parse it through parse option, and then pipe it through map, and then we have the function. Great, right? So this is pretty readable. We take the string, we parse it, and we map a function over the result. So great. We can also, let's say, when we have the function, a function we map over is already defined. Let's say we have +1. We don't need the lambda here. It gets even more readable. And let's say we have another thing we want to chain onto this pipeline. Let's say we define a function which is called toString, which takes an integer and performs toString on the integer. Well, what can we do now? We can extend our pipeline. Let's say this is our pipeline. We map +1 over it, then we map another function over it. In this one is toString. So great. What we can see here now is we have really a composable library already, in multiple lines, so that it's easier to read here. So each step produces an option, and then uses map and a function to continue the computation. And this is really completely without having pattern matches. However, it is totally safe. If one of the steps fails, the end result is none. Let's try it out. We have here our parse +5. Let's say we start with 6, and we get 7, but this time as a string. And as you might see, this already remembers us totally it looks pretty similar to LINQ, where we had, or list processing we looked at the last time, because here we really have a pipeline, and each component is just a combinator which can be used to build a more complex program. And just to complete on this, you can also write it differently. Like here we can say, okay, we have parse plus 6, and we can now write it as function composition when you say, okay, we have map and here we have map. So why not making plus and toString in one component instead of having multiple maps? Well, this is doable as well. Let's say we parse, we take our input as, we map it through parse option, and then we map it by using +1 and then toString as a function composition, and we end up with the same result. And we arrive with 100. So awesome. This is the first time we have used a function composition, piping, higher order functions, pattern matching, in order to really write condensed code which deals with non-existence of values without having the struggle of checking the existence of the value every time. Oops. Again, I just lost the track here. So what have we seen? We have seen that discriminated unions can be used to model non-existence of values. We have higher order functions, and we have piping and composition, and it really looks similar to LINQ. So what we have seen now is we have seen discriminated unions, which are actually the first ingredients of an algebraic type system. And then there is the second component, which are tuples, records, and stuff like this. The first one, discriminated unions, is called a sum type because a value can take several different but fixed types. So it can either be none, or it can be sum, or it can be, as we have seen before with barcode, this option, this option, this option, this option. In tuples, we always need to have all values in place. For tuples, each component needs to be there. So let's look at tuples in F# here. Tuples can be constructed. Again, please note the notation of construction. The first one is we can construct an empty tuple, which is just empty bracket of open bracket and close bracket, and this has a special name. It's called unit. However, we can also create a single element tuple like this one. Here we only have one argument, and we create a tuple with one element. Rather useless. So we have 2, and we have 3, but we can also have nested in such a way. This is now a tuple of integers and an integer. And what we can see here is that those tuples can be constructed by using this notation, and they can also be destructed. So here, let's say we have A, B, and this is 1, and 2. Oh, we already have A's and B's in this file already. So let's take it X and Y, which is even more appropriate. Let's say okay. And what we get here is we construct a tuple 1, 2, and then we destruct it and assign it to variables X and Y. So this is pretty cool. What we can also do is we can write functions. For example, let's say we write the function first, which takes an argument, whereby the first part of the tuple is interesting and the second one doesn't matter for us. This is the wildcard pattern match. So everything matches here. And well, what we arrive here, what we return is the first component. Analogously, we can define another function which is called second, where we're not interested in the first component but the second one, and return the second one. And what can we do with this? We can use those functions. For example, when we want to extract the first one, we get 1, and when we execute the second one, we get 2. So those destructions can occur also in functions. And actually, as we have seen before, destruction is pattern matching. However, here we don't have different constructors we need to pattern match for. We can only match for the single case, which is the tuple of the right arity. And yeah, this is pretty cool actually, since it can be used to write very succinct code. What can we what's about those wildcards? We can also write patterns like this. So here we have the construction, and here we have the destruction of the tuple. Will this work? Yes, it works. What happens when we say, okay, we pattern match, we construct a tuple in such a way, and we destruct it in this way? Now we get a pattern match exception, since we use pattern matching to deconstruct a tuple, but we require it to be the tuple of a particular kind with particular values, and those do not match, those two. What we can do here is we can, for example, put in 3, and this is the wildcard pattern match here, so this matches every value. And again, let's execute it, and this one works. This is not really that useful to have pattern matches on tuple types which might produce a pattern match failure. We rarely do this. However, I just wanted to show you that we really have the construction and the destruction, and it's really totally the same as we had it in the discriminated union case. And does this work in other languages as well? Yes, in C#9, for example, you can write a function like this. Here we have a function which takes a tuple and returns an integer. And this function should be the same as second as we defined it in F# just right before. It takes the tuple, then performs a deconstruction. We take the second value and return it. So this is a appropriate implementation of second. It's not that flexible right now, maybe in C#10, when we can write the tuple deconstruction here on the argument side. So what's the further story of tuples and product types, which is the generalization thereof? Records are just tuples with names. So we can define a tuple here with 2 arguments. However, each component has a particular name. What can we do? For construction, we can just write those braces and define every component of the named tuple, so to speak. Here we get a rectangle. The deconstruction is again completely the same syntactically. So here we pattern match for this rectangle as we did it for the tuples before, and here we get the v and the h as available in our as a variable binding. So let's say we define the rectangle. Mixed up rectangle is the width of an integer and the height of an integer. Let's write it out. Let's define a function foo which extracts, for example, the width of the rectangle. What can we do now? We can use a deconstruction of the rectangle. We can say width is, and the height is. We don't take care of this one, and then return the v. And here, is there already a foo? Of course, there's already a foo. Let's define it this way. Now we have it here. Foo2 of width is 10 and height is 0 in that case, and we arrive with 10. So again, pattern matching deconstruction, it's everything is the same. But you can also do it like this. You can access the components of the rectangle directly. Let's say we get in a rectangle, and then we just perform r.width by using dot method access, and again this works. So what we basically have here now with tuples at hand, in the last lecture we learned about carried functions, where we used nested functions in order to model a function with multiple arguments. So this was this variant here. It's actually a function which takes an integer, which creates a function which takes an integer and produces the sum of those. You can also write it in a tupled form. Actually, it's just deconstruction here. It's not a special case, so to speak, and then we perform the addition. So tuples and carried functions can do very similar things. However, the carried functions are more favorable in functional programming since we can do partial applications with them. Sometimes we have functions which are simply not carried. Let's say we have the function add, which is not carried because another one. We can write a function. Oh yeah, we can of course do it by hand. We can say okay, add, which is now a carried function. We can call the other one by constructing the tuple and deconstructing on this side. But we can also do this generically for every function. Let's say we define a function, it's called carry. It takes in a function, a value, and another value. And then we just create, we call the function we just got and give it a tuple. And here now we have the carry function. Look at the type of the carry function. It takes in a function which takes a tuple and returns C. And what we get out is a function which takes A and returns B. When we write it in with parentheses, it's a little bit easier to understand. So what we have here, I'll just write it for clarity. This is the argument, and then it returns. It returns actually a function which takes from A to B to C. Oh, here I did a mistake. The function takes is of course from A start B to C. It's hard with this size of the fonts. So it should work. It does not work. Oh, I wrote it wrong. I have no arguments here anymore. With this explicit notation, we need to write it like this. Just to not to have any confusions, the old version was FAB and then FAB. And when I write it this way, that it takes a function and produces a function, I did not introduce any arguments here. This was my mistake, so I need to have a lambda here. But as we already know, it's possible to, instead of having a value which is a lambda, we can also put those arguments as parameters here, and now we have this function definition, which has actually the same type. However, as we have noted already, the functions can be written without parentheses. So this actually completes the algebraic type system. And in the next session, we'll do something more useful with it.